The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
So, very brief recap of where we were in the last lecture. We talked about electronic band structure in crystals. Right? The lecture before we said 1D, and we briefly extended to 3D. No extension, just show you how 3D look like. And then we start talking about real crystals, Bravais lattice, and the crystal bonding, how the crystal, different type of bonds, van der Waals bond, ionic bonding, covalent bonding, metallic bonding. And then we talk at the end, we say reciprocal space, right? How we represent periodic 3D functions and using the Fourier transform. And for that, we need, say, the inverse of this in 3D. Fourier inverse is in the reciprocal space. So if we have real lattice, real space lattice with the primitive lattice vectors A1, A2, A3, we say the corresponding reciprocal lattice vector is B1, B2, B3. Well, B here, B1 is A2, A3. And B2, you will just permute the index. So B2 is A3 cross A1. Right? So with that, you can construct, this is the primitive lattice vector. You can construct array of points using the reciprocal lattice vector G. And this is this is the way you construct a reciprocal space. And correspondingly, you have a primitive unit cell in reciprocal space, and also Wegener-Seitz cell. That's a unique way to construct a unit cell, primitive unit cell, right? And Wegener-Seitz cell, there's also another limb. Is this smallest volume is the first Broglie zone. And now, if you take real space lattice vector T, which consists of integer n1, n2, n3 combination of a1, a2, a3. And you take the reciprocal lattice vector G, and you do their dot product, and you'll say, because of the characteristics, this is the volume of the real space. So because of characteristics of this cross product, you'll find out that G dot T is just 2 pi times the integer. Okay, so that's those are purely the reciprocal space. I was joking is really mathematical concept, right? It's a Fourier transform of real space. And so I say it turns out it's much easier. Like when electric engineer always use frequency, and physicists like to represent everything in the reciprocal space. And also, at the end of last lecture, I talked about the Bragg condition. Right? I give you, if you have a periodic structure, you have a wave comes in, and I have a crystal, for example, and the wave comes in. It could be X-ray, it could be an electron wave. Right? In transmission electron micro, say Scobie, you use electron wave, and X-ray, you have photon waves. And you use a detector. So a wave has a wave vector, K incident. Let's say this is the final outgoing wave vector, right? And it turns out if you have a periodic structure here, crystal, and the condition where you can detect, this is your detector, this is your source. The condition you can detect a signal is when Ki minus Kf plus or minus G equals 0. So this is the Bragg condition. Okay, and gave this at the end of last lecture, and we went to Google image and look at a lot of diffraction patterns. And for X-ray, we do 2 theta, measure the diffraction peaks, right? So for me, always here is where I struggle a lot, whether I want to actually go through the proof of the Bragg condition or not, and because it's a little bit mathematical intensive, but I still want to do it. And so next, I want to give you a mathematical proof of Bragg condition. And it's conceptually is not that difficult. I have a wave comes in, so I can represent the wave in vector form, right? So a plane wave, if you recall, we gave so whatever wave, this could be an X-ray, a photon wave, could be an electron wave. So a wave is a wave vector ki, right? And the direction, the coordinate of this wave I'm considering. So I want to look at a specific point r. So if I take here, right, this is my coordinate system. And this is from here to here is my r. And let's say this is my source, right? So I write this is my ri. So the vector between this point and the source is r minus ri, right? That's from source to the point in the crystal. So this is the distance, the direction that the wave propagated. So k times here r minus ri. So this is the wave, a plane wave that traveling towards a point r in the crystal, right? If you see this point is an atom there, X-ray comes in, the atom can scatter the X-ray. Same, if it's an electron wave, atom there, the electron interact with the atom and the electron gets scattered, right? So I will get scattered. So I have, let's say, the signal, the scatter signal, of course, is going all direction, but I'm looking at my detector is placed here, so I want to look at the scatter wave into this direction, into direct detector, right? And of course, say the scatter depends on the weight of the atomic structure, the electrons, neutrons of the atom itself. But I'm not going to care, so I say this is a scatter amplitude of that scatter wave, right? And I know it will be proportional to the density of the atom, meaning the number there. If I have an atom there, it gets scattered. If I don't have an atom, it doesn't get scattered, right? So in the crystal, I have a location for these atoms. And the scatter wave come back to my detector. So let's say this is r. This is from here. You say this is my vector, rf. So the distance traveled between this signal between the scattering point and detector is rf minus r. So this is ikf times rf minus r, right? So this is nr is at each r point, but of course when my signal comes in, I have crystal, I have many atoms. So I have to, the total detector signal is the integration of the each atom, say how much signal is scattered to my detector, right? So I will integrate this signal. This is the incoming, this is scatter, right? So it's I will integrate over the volume of the crystal. This is what I get, signal at the detector, right? Again, I see some puzzle here. This is a plane wave comes in. This is a plane wave scattered to the detector. And this is where I have an atom there. And this is how many atoms I have in the crystal. Right? Now, this is a crystal. So the arrangement of the atoms is periodic. Right? So here I say NR. And in 1D, if it's a periodic Fourier function, you know how to do the Fourier series as sine, cosine. And in 3D, the Fourier expansion is NG. This G is my reciprocal lattice vector. And it sum up all those points and exponential minus I R times G. Okay, so this is the expansion of a periodic function in the Fourier space, reciprocal space. Okay, and you can prove it if you do R plus T. T is my periodic function in real space, right? Because this atoms is periodic arranged. And if I do G and G, I substitute in is minus I. R now is R plus times T times G. You can say T times G. T times G is 2 pi times the integer. Exponential 2 pi, I 2 pi, is 1, right? So if you do your math here, this essentially is NR. So that says my atoms is periodically arranged. That's why I say this is the way I expand 3D periodic function. In this case, is atomic location in the reciprocal space, the Fourier space. Okay. So with this now coming back, this is a digression. Let's say my NR I can expand in G, right, into sum of G. I still have to do the integration over the volume for this R, different R, right, different points in the atom. So now I substitute this N in terms of my expansion. G is the sum, so I have an integration, volume, and the sum over G. I can invert, I can exchange the order. So if you follow my math, what I will write next is I exchange the summation after I expand the N in terms of G, and then I exchange the summation with the integration. So what I have is G, and then say exponential. So all those coefficients A times S, I just space independent, and I will have I, K, I, and Ri. This is a plus. If I look at my first exponent, these are the irrelevant exponent, because it's related to position of detector. So I have IKF times RF. Right? Those I said those are irrelevant. It's just factors. Depends on where you put the detectors, where you take your coordinate. Right? What's relevant is now, as I said, I switched that integration with the summation. Right? I put the integration now here, and what I really have, because this is integration over R volume. Right? So this term I have Ki times R. This term I have Kf times R. Here I have R times G. Right? It's all exponential functions. So now I have exponential minus I, Ki. If you write all them together, minus Kf. Here is plus G times R d volume. So this is what matters here. Right? And what you see here if you plot this function, exponential function, right? So I is sine cosine, right? What happens when you add many? You see, this is a volume. A typical crystal has 10 to 23rd atoms, right? One more. I'm just giving you that number. If you sum many sine cosine, what do you get? Say each one there is a small difference, right? The position has a small difference, right? Incident wave vector, say the detector wave vector going to detector, reciprocal lattice, those are constant. So if you sum many sine functions, you get 0, right? You get 0 most of the time, except when this exponent itself is 0, right? So the only way, so if you put a detector here, what it means, if you put a detector in if it's not in the right position, you don't measure any signal. That's the diffraction. That's why you see these spots last time when we showed the TEM, right? So this one, essentially the condition here is this has to 0, and that's my Bragg condition. Okay, so this is a little bit mathematical lengthy, but the point I want to say is, if you see when we introduced before the plane wave, we say we can always represent a wave by expanding it into plane wave. So this is a vector plane wave representation and scatter wave, and using the periodicity of the crystal, right? Anytime you have periodic structure, you can have a diffraction effect, right? And let's say if I have so this is a vector. Now I can give you an example where I have layers of atoms, right? In any specific direction of the crystal. I look at say there's periodic planes of the atoms, right? And I put an X-ray coming here at the angle theta, and this is my incident X-ray wave vector, right? And now this is sort of my 1D plot. My periodicity is A. So my wave vector, say the reciprocal in 1D reciprocal lattice vector is in the periodicity direction. Here I have 2 pi over A. This is a 1D, right? And times n. Okay? So now I write Bragg condition because the 1D, the wave vector, the reciprocal lattice vector is 2 pi over n in this direction. So I do my component. So what I have is Ki is 2 pi lambda I, a lambda incident photon wavelength. Let's say this is incident angle, theta I. So it's a sine theta I. That's the vector component in this direction, right? And my G is in this direction. So, I put my detector in X-ray is typically, this is your source. You put the detector symmetrically on the other side. So this reflected angle equals incident angle. So that's a 2 theta scan. If you use X-ray, people say, what's your 2 theta scan? Rocking curve, right? In that case, what you do is you rotate your crystal. And different rotation crystal, you are rotating different plane to meet the Bragg condition. And here in the reflected direction, so you can see my wave vector is going back. So in the G direction, I have a negative here, right? So my is when I do Ki minus Kf is actually I have again the reflected wave vector is sine theta I, same as the incident because I'm looking at the 2 angle position the detector symmetrically, right? And then say plus minus g, so I can essentially write that as 2 pi a times n. Okay, so here you can say I put them together. I have sine theta I and a and 2 equals n lambda. So this is when you put your detector in typical X-ray, you say incident, reflection, you put them say equal angle. And when you measure peak, you know the angle, you know the wavelength, then you go to determine the lattice spacing in that specific direction, the lattice constant. Okay? So that finishes our discussion on the crystal structure, reciprocal lattice. And now let's move on. So we talk about the electron. The next we want to talk is the atom vibration, the photons. Okay, in crystal. So the crystal, the electronic structure in crystal. So what we have next is lattice vibration. And the photons. Okay? So if you recall, we in the few lectures ago, we say hydrogen atom has vibration relative to each other, right? And when we treat that vibration, we use say a spin to connect them. So in general, the interatomic potential is repulsive, attractive. We talked in the last lecture, right? And at the equilibrium point, if you expand your potential, because first order derivative is 0, right? So you will have 1/2 kx squared. Okay? And with that, you see your and the higher order terms, but this x is the displacement from the equilibrium here, right? So the force, the nearest order force is du dx, and that gives me a linear spin. So when we deal with the hydrogen atom, a model, a hydrogen, say molecule, a model is a mass attached spin, and in that case, we know, again, this is a confined wave, right? Hydrogen molecule, the vibration is local to the hydrogen molecule itself, and the vibrational frequency is k over m. Right? It's classical, and also the quantum. What the quantum tells us is really the energy cannot be any number. It has to be h nu n plus 1/2. That's what we talked before. Okay? And now the question is, what about when I have a chain of atoms connected by springs? Right? So I'm looking at a simple picture as we deal with the electron. I have one-dimensional atomic chain. And in the case of electron, I look at the potential Coulomb interaction between the electron and the nuclei. But in the case of the atomic vibration, I'm looking at the force interaction between the two neighboring atoms. Right? And my model is simplest because I'm only saying I connect the atom only to the nearest neighbor. In reality, if you think about the ionic potential we wrote before, one positive ion, one negative ion, you can have force Coulomb interaction, but it could also have a next negative ion or positive ion could also have direct force interaction, right? So I could have a larger spring connect from here to here. But I'm not doing that. My simplest model is only connecting my nearest neighbor, And now I want to find out what's the vibrational energy of this atomic chain, right? And I could go to write my quantum mechanical form, because if you recall the Schrodinger equation, what we need is a potential constraint, right? And that's what we essentially said. If you do a harmonic oscillator in the hydrogen atom, you write your potential, and we derive without solving the Schrodinger equation. That's my my own way of solving Schrodinger equation. You have this vibrational energy quantization, right? If you recall that. What we're going to do, so if you do that way, it turns out that your vibrational frequency will be the same as you solve classically. Essentially, this is the same. In the hydrogen molecule case, this frequency is a classical frequency of any oscillator. What we have here is just energy quantization, right? So because of that, I'm just going to solve the Newton's second law. I'm going to solve it classically and get the frequency, and then just introduce you similar to if you do quantum mechanically, it's just at each frequency your energy is quantized. Okay, and so it's two different approach. You get the same result. And what we're going to look at now is the atomic displacement. So if I have an atom I here, right, and the ui is the displacement, so is the xi is the coordinate, right, minus xi0. That's the equilibrium position there. So this is just a displacement of atom I. And I'm going to write the force I plus 1, I minus 1. So I have the force equals the at the equilibrium, that's the minimum point. So it's really the relative difference in the displacement gives me the real stretching or compression of the spring, right? So when I write F equal ma, and I'm looking at the vibration, because the 1D is constrained, so I'm not looking at the other plane vibration, out of chain vibration. I'm looking at the in chain vibration, right? So I'm going to write M, the mass is the same because it's identical atoms. So I have mass and d ui, so ma, so dt squared, F equal ma, right? So this is my ma term, and my force term is I'm looking at this is the positive x direction. So this force is positive in this direction. So I have k spring constant u I plus 1 minus ui. So that's the relative displacement of the between I plus 1 atom and ith atom, minus this force is if it's I minus 1, so that's this direction. So I have minus sign k ui minus ui minus 1. Right? So that's my F, the force acting on the atom I, ma. Okay, so now I just need to solve this simple discrete equation. It's not a continuous equation, right? Because the atom is a discrete point. And if you solve a continuous equation, you see what's the corresponding continuous form. If I write this one into k ui plus 1 minus 2 ui plus ui minus 1, right? If you do finite element or finite difference analysis, you know this. If you have a continuous equation, that's the second order derivative, right? This will be the second. If you discretize du dx squared, you will get a form like this. Of course, divided by delta x squared, right? So if you look at this, if I write continuous dt squared dx squared, that's a wave equation. Okay? Right? And wave equation, if it's, say, again, in the continuum limit, my solution as a function of x will be a wave equation, simple solution omega t minus kx. Right? This will be the continuum solution. Now I'm just going to use this try to see whether I can, my discrete solution will still follow this form. And in that case, xi, so the position of xi, this ith atom, the x location will be I times a. Right? That's xi. And so I'm just replacing xi plus 1 is I plus 1 times a, and ui I plus a, and going into the equation. So my left-hand side is the time derivative. So ui omega square, right? So what I have here is m, the second order derivative with respect to time, gives me a. And what I have here, minus I omega square, so it's minus omega square, right? And exponential minus I omega t minus k. My notation is a little bit troublesome. Let me write this as j, because I don't want two i's. Okay, j. Okay, and then say I have k is my wave vector, and x is I times a. That's the left-hand side, right? And the right-hand side equals k, and you can say my a will all pull out. And exponential here, I have a common is really x equals I. Here is one less, so what I have is 1 plus I k times a minus 2 plus exponential minus I k times a. That's here is 1 less in coordinate, and exponential minus I omega t, j times omega t minus kia, right? I pull out a common factor among I plus 1, I minus 1. That's my common factor pulling out. And the first one, I have I plus 1, so it's extra extra j times a. And here is 1 less deficient, because u I minus 1, so it's negative j times a. And this is a j here. Oh, I. This is I. No, I'm confused. Okay, right? And so you can say this one, these two factor cancel, a cancel. So I get an equation for the eigenvalue of the vibrational frequency omega. Okay, so this cancels, and a cancel. What I have here is m omega square and negative, and I have here k and e j k a plus 2 plus e minus j k a minus 2. E j k e minus j k a gives me cosine, right? So 2 cosine ka minus 2. That's on the left-hand side. I have another minus sign here, so I put the 2 in the front. So I have omega squared equals k times m and 2k, because that 2 I can put out, 1 minus cosine ka. Right? 1 minus cosine ka is what? Sine 2 times, right? 2 times sine 1/2 ka. Right? So I take the derivative, take the square root. So my omega, then the vibrational frequency, I always take a positive. So omega is 2k over m, but then I have to take a positive ka over 2. So this is the vibration frequency of one-dimensional atomic chain. Okay? And how does it look like? It's a sine function, essentially. So when ka over 2 is half pi is maximum, so let's plot this. So what we have here is really the vibrational frequency. This is a Ka. So this is the frequency of vibration omega. And the Ka, so when Ka over 2 equals pi over 2, that's the maximum. Right? That means the K equals pi over A, that's maximum. Right? So if I write this K, here is pi over A, is the maximum, and this sine. And on the other side, negative side, is again, say negative pi over A, and is also sine function. It's symmetric. I didn't draw it symmetric. Right? Okay? And of course, you can extend to any k values. So this is what the mathematics tells us. And now let's think about what does the physics tell us. So first we want to say what's the value of k. Right? What are the allowable values of k, the wave vector? Right? And for that, again, I can use two concepts that I have been say talking for electrons. One is a finite length of whatever vibrational wave between the length of the crystal, and you do your Fourier transform. Right? You do your Fourier expansion. The other is the von Karman periodic boundary condition, and the two are really equivalent. So the von Karman periodic boundary condition say the first atoms here, and they should equal to the vibration of the nth atom. Say this is Na. That's the length of your crystal, right? And with that, you use the Bloch theorem. What you have is minus k times Na. That's N is the total number of atoms equals 1. That's what we used for electron waves in 1D case, right? And that means k times Na equals plus minus 2 pi plus minus 4 pi, all this, right? So k then, if you divide it back, here is plus 2 pi over Na and 4 pi over Na. Let's continue. So if you count, is again when Ka times is whenever it's really 2 pi here. So before I say for electron, between minus pi to plus pi over A, I have n points, right? That's the case when I have n atoms in the chain. And that's the same. If you do this, you'll find that between minus pi over A to plus pi over A, each point of this K represent one waveform, one form of the wave in the crystal, right? So if you go back to quantum mechanical, that's one quantum mechanical state of those vibration. So between minus pi over A to plus pi over A, I have n points. Okay? So that's the K. What are the K? And secondly, if you think about in the case of electron, because of symmetry, we actually only draw between 0 to pi plus pi over A, right? The negative side is symmetric, and go beyond this is repeating. So in the case of electron, because K is the other way to think about K is 2 pi lambda. That's the wavelength, right? So for Phonon, in fact, this waves really doesn't mean anything new, even from the wave vector perspective, because if you look at I have lattice vibration, right? And the wavelength, if I have K equals pi a, what does that mean? Is lambda equals 2a, right? In this point, my wavelength is two atomic distance. So that's my wave at this point. Now, if I go to 2a, pi over 2 pi over a, what's my wavelength? My wavelength will be this, right? My wave. This wave, there's no atom moving at this location, so you plot a minimum here, a minimum here, means nothing. So physically, in the case of atom vibration for lattice wave, I'm limited between pi over a to plus pi over a, negative pi over a to plus pi over a. And there are, if I have n atoms, I have n points between this, say, first Broglie zone. So still the reciprocal lattice. Okay? So this is the first point. And now I'm going to extend. So here I have a simplest 1D atomic chain, monoatomic. Every atom is the same, right? So I'm going to extend this picture of the vibrational normal modes, the frequency. And let's think about diatomic chain. Again, it's 1D, right? Why I talk about diatomic? If you recall in the last lecture, I say in a silicon example, silicon crystal, right? Each lattice point, I actually put 2 silicon atoms, right? And sometimes I put 3 atoms, right? So now I have a crystal 1D. This is again my periodicity A, right? But I could have another atom, even identical, but it could be different. Gallium arsenide is another example, right? Those are 2 different mass. Even same mass in the silicon, one silicon is closer here than here. So I could have, so my Now let's say diatomic atom. So this is a one type. And then I have another type atoms here, two different mass. Okay? And but say my period of the crystal is A, and I have one spin constant, another spin constant. It could be two different spin constants. Right? So in one unit cell, I have two atoms. Okay? So in that case, you can go back again, write the F equal ma. But you have to write two sets of equations. Each set is for one specific type of atom. And these two sets, of course, are coupled, right? So what you have, I'm not going to write it down, but the solution, what the solution will look like is, again, I'm writing my first Brownian zone, pi over A. This is a K, right? And this is omega. And we have still the bottom solution we draw, sine function. But I get an extra branch because I have two atoms per unit cell. Okay? So the, what this two branch mean is in this branch, a more intuitive picture is the vibration is all in harmony, right? So this when this one atom vibrate here, this atom vibrate here, this one is here, this one is here. That's the lower frequency branch, okay? And now the other, the higher frequency branch, right? Same wave vector, so I don't plot my different wavelengths. In that case, so this atom is vibrating up. This, so it's opposite. So this atom now going here, and this atom going here. So it's say one is sort of in phase. The lower frequency one is all the atoms, two types are in phase. The other one is more out of phase, right? And out of phase is higher frequency, and in phase one lower frequency. And this is also, as we extend the phonon, h nu is the vibration, the vibration quanta h nu is a phonon. So higher frequency one has higher energy. Okay, so when they, so that's the two different vibration here. This is acoustic mode, and this is the optical mode. And so later on, as we add a phonon, so this is acoustic branch, acoustic phonons, optical phonons. Okay? Yes?
Is there a reason for those names?
Well, so optical is when you have light, some of the light, because a higher frequency, so infrared light, for example, could interact easier. You have to have when you have the photon interact with the atom, the energy has to match again, okay. Right? So glass, SiO2, right? The glass, why you have greenhouse effect? Because the vibrational frequency is about 10 microns, and the light emitted in this room is about 10 micron, and light hit the window and get the resonance between photon energy and say vibration there to get absorbed. So the energy doesn't escape. That's your greenhouse effect. Okay? So now we have acoustic branch, optical branch. I'm going to pile more onto it. It's 1D, right? So in the model I have, the vibration direction is the same as the wave propagation direction. What is that wave? Longitudinal, right? That's the sound wave you hear. Sound wave is a longitudinal wave. But if I relax to say this atom can also vibrate out of this Chen direction, I got the other motion, transverse motion, right? Do you think that it's easier to do this way, longitudinal motion, or it's transverse? Transverse?
Easier. What do you mean?
So in terms of the modes, well, this is softer. So Chen, if you say atoms there, is it easier to vibrate this way or vibrate this way? 1D. A Chen is probably, if you think about one-dimensional atomic Chen, right? It likes to fold, right? That's a transverse direction, right? It's a lower energy. So now if I do transverse, I can decompose the transverse into perpendicular direction, right? So in general, so if I relax to 3D motion, I only draw now, say, 0 to pi over a, and remember there's symmetry negative is the same direction, right? So what I have, this is longitudinal, and this is transverse, right? And the other comment is at the zone center, the boundary here, right, is my maximum. So this gradient here is 0. Typical vibration, those say energy or frequency dispersion relation at the boundary is perpendicular. Okay, so here I have longitudinal acoustic, longitudinal acoustic branch. I have transverse acoustic branch. Okay? Yes?
Why is there two?
Huh?
Why is there two transverse acoustic?
Well, so, okay, this is the wave propagation direction. If the vibration is this direction, that's one. Vibration into this direction, that's the other.
So why are they different?
If it's a 1D Chen, it doesn't differ. But in 3D crystal, in one direction vibrate, and the other perpendicular direction, they may not say the right environment. Okay, but say you're right. In many cases, they actually degenerate if if you look at two perpendicular directions, they are the same. So you actually say one line, but that actually implies there are two branches that's degenerate. Remember the degeneracy? I'll come back to that degeneracy again. After we discuss all those dispersion relations. So this is acoustic. So here I have optical, 3 branches. Say again, transverse longitudinal branches. Okay, and so that's the going from 1D, monatomic, diatomic, to 3D. And of course, this is 3D is say 3D in the sense that I consider one wave vector direction. Now you go to crystal. In different direction, you plot the different sets of curves. Okay. And so here, one more. If I have m atoms, so here is a diatomic, right? So if I have m atoms per basis, so the lowest 3, so I have I have n points, lattice points, right? So now you do your counting. I have 3n acoustic branch. So the lowest branch is acoustic. Acoustic modes, not branch. 3n acoustic modes. Right? Because here between negative pi over a to plus pi over a, I have n point. I have 3 branch, that's 3n. Right? And then I have the rest is 3m minus 1 times n optical modes. Okay, so optical modes, the more atoms you have per unit per lattice point, the more optical modes you have. Okay. Now this is all continuum mechanics, or not continuum mechanics. It could be, but it's a classical mechanics. F equals ma, right? But it could be atoms, so it's a discrete but classical mechanics. Now, what the quantum will add is like what I commented before. The energy at each mode cannot be continuous, right? And normally vibration energy is kinetic energy plus potential energy. You add, that could be a continuous function. And what quantum tells you at each mode, each frequency, or each mode, and at the frequency, the energy of that mode is 1/2, say h nu times times n plus 1/2. Okay, and again, this 1/2 is say 0 point energy. Zero-point energy is actually a requirement of the uncertainty principle. Because here, when we draw, I can't say the atom is exactly here. If it's exactly here, its location is fixed. Heisenberg uncertainty principle will say its momentum is expanded to infinite, right? So because of that, this there is always this 1/2 h nu, that's a 0 point energy. And there is, in fact, some connection of this to the force interaction between, it's the fundamental, so it's van der Waals force is equivalent to this 0 point energy. There are some interesting connections. So that's this is what the quantum. If you solve your Schrodinger equation with the potential, harmonic potential, and you get all the dispersion same as the classical, but you get the energy quantized. We didn't take that approach, right? So this quanta h nu, that basic energy quanta, is a Phonon, same as the energy quanta h nu for electromagnetic wave is a photon. It's not an electron like an electron, right? So photon are bosons. And the spin is an integer spin. Electron is a half spin. And electron obey the Pauli exclusion principle. So each quantum state can only have maximum electron. But each quantum state, right, here, this k for a specific k value represent a wave function, a vibrational wave function. That's quantum state. Each quantum state can have n, could be 0, 1, 2, infinite of phonons. Okay, so those are bosons, and it's fundamentally different. And it doesn't have a rest mass. Electron has a mass, right? What's the mass of photon? There's no rest mass photon. It has a momentum, it has an energy, right? So you lock at it, you can create the pressure, but doesn't have a mass. It's a collective vibration. It's a collective modes. So I joked. I had once a colleague say after he sit in my class, I still don't know what is a phonon. And it's a fictitious particle. Sometimes people say, right? It's not a real particle. This is a phonon. It has energy, and it has momentum hk. And in 3D, it's k. Or energy, sometimes we write as h bar omega, right? Your h nu depends on whether you use nu or omega. Okay, so that's the photons. And now you go to, like I said, you go to real crystal, you'll see different photon, different direction have different dispersion. So again, I will go to Google to show you those complexity in real crystals. But before we do that, let me introduce some approximation. Yes?
How far out of equilibrium would you have to be so that your original approximation that is just a harmonic oscillator doesn't hold anymore?
My original harmonic oscillator. So, very good question. I remember, for example, I just mentioned glass, right? It turns out that I also mentioned the hydrogen atom, right? And it turns out that in physics, when people talk about photon, they talk about the extended modes. So hydrogen atom vibration, people mostly do not call it a photon. And once I went to a photon conference, and I asked, say, a very famous guy, say, what about the photons in glass, right? Because glass is not periodic, it's not a crystal. And nobody knows, he said. All right, but it still have those modes. And but say you ask, there is even more profound question one could ask in this direction, because when you go to third term, right, here a potential is a harmonic, right, second term. Go to third term, that's the scattering. That's the two photons start to couple. And this is in fact very different for light. Light normally hard to couple to each other, right? And by photon, you easily couple to each other because of this third term. But if that third term is so strong, right, and it can come back to affect your dispersion. And I do not know good ways to do it, but there are people, publishing paper, for example, recently there was a paper on the soft photon in telluride. And because of the strong unharmonic interaction, that change a lot on the photon dispersion. Then the question is, if the photon scattering is so strong, it breaks the wave, right? I say this basic picture is I have extended wave through the whole crystal. But say if it breaks the wave, it doesn't say if the inverse of this frequency is give you time for one period of vibration. But if the event to break this say wave is even faster than the one period, then I don't see how people, I do not know how people are describing those. Okay? Let's say the next is the approximation. If you recall, for electrons, we say at the bottom, right, we use a parabolic. We say at the bottom in this region, the first order dispersion, the first order derivative is 0, right? And so I use a parabola to represent electrons. And for photons, for optic photon and acoustic photon, you look at it, it's like a sine function, right? And then the simplest approximation that people have made One is a linear function rather than that sine function. And this is the other is flat. That's more appropriate for optical phonon. And this is more appropriate for acoustic phonon. And this approximation is the Debye approximation. And this is Einstein. It turns out that the Einstein first created this model to model the specific heat of a crystal. But say it's not valid, say it doesn't agree with the experiment when you go to very low temperature. That's because when you go very low temperature, most photons are here. And so the specific measurement doesn't agree. So Debye introduced the linear dispersion. So those are two different dispersion. And the corresponding frequency, this is the Einstein frequency. This is the Debye frequency. And in a real crystal, the Debye model, very often we will do the, later on we'll talk specific heat. People typically use the Debye model. And this K, right? Well, of course, I only draw 1D. But in real crystal, is different direction, have different K. But the Debye model actually is an isotropic crystal. So it approximates not only linear in one direction, just use one direction represent the whole crystal. So that's with that, there are some relations in terms of you convert what's the corresponding Debye lattice constant here. You have to count the total modes to be consistent. Okay. So where we're going from here is in the next lecture, I'll continue come back to say use this simplest approximation, the Debye model or Einstein model, to count degeneracy, right? Before, when we talk about the say hydrogen atom, electrons, right? We say degeneracy is 2n squared. That's how you understand periodic table. Okay? But now if you look at this, if I draw it in one crystallographic direction, this is a pi over A, and in another direction, there could be another dispersion, right? So this represents a different mode, but they could have the same frequency, right? So that same frequency means the same energy. And I can have many modes that have the same energy, and I have to count that degeneracy. And that counting is very important if you want to do any calculation. It's a mathematical concept. That's the density of states. We're going from degeneracy to density of states. And that we'll do in next lecture, so I want to use the rest of today. Let's go to do our exercise. Say what we have learned. Okay, so I want to do a few things. First, I'll continue to look at the 3D photon dispersion, right? I mean, so we talk about very simple models. But when you read any paper, you look at those lot of curves inside, right? You will say it's just a plot in different crystallographic directions. And we'll also then go to look at the relevance. Let's look at some papers. Okay, so first thing, I'm going to use my desktop. So let's first look at the that's my last homework. And I have trouble. Let's do this. Google, I have a little bit probably using this different way of putting the sidebar Google image. And I want to look at the photon, silicon photon dispersion, right? So now you look at the silicon, right? This is when we say QQQ, that's 111 direction. And this is 011 and 100. So since silicon is a cube, right? 11 direction is diagonal direction. 100 is the any of the main edge direction, right? 100 is the 011 is if you think about a plane, let's see. Right. This is your 100 direction, and this is a plane of 011 direction, and here is the diagonal is 111 direction. Okay. So you can see here in 100 direction, the two transverse photons degenerate into one, right? And the longitudinal photon. And here you have optical photons. And but say in the 100 direction, you don't have that degeneracy. So you have two transverse, one longitudinal, right? And in the optical. Okay. And let's go look at the silicon electronic. Silicon band structure. Okay. Here, again. So now you have to say this is a gamma to L. That's the gamma to X is one. I think that's the 111 direction, and 100 direction, and this is where the topmost. If you do zero temperature, this is the electron, uppermost electron, the Fermi level, right? So this is a valence band. Those are the valence bands. Here is the conduction band. That's the lowest. You see, that's the absolute gap, right? Between here and here is the minimum. That's the band gap. And it's an indirect, the minimum and maximum, not at the same point. Right? So a photon comes in. If you want to lift the electron from here to here, that's an absorption process. It doesn't have enough momentum because there between here and here is a big k. Hk is the momentum. A photon momentum is very small. So it's harder for photon to be absorbed in silicon. Okay? And if you look at the electron for gallium arsenide, right? Gallium arsenide band structure. Okay? And maybe this one. You see the minimum. This is not this is not nitride. Gallium nitride. Right? So let's look at the. This is not all directions. This is just a drawing 111, 100. But the minimum and the maximum, this valence band, conduction band, is at the same k vector. That's a direct gap semiconductor. See, there you actually have. You see that here there are different bands. right? These are the whole valence band holes, and different bands have different mass, effective mass. This is lighter, this is heavier mass. We talked, say, effective mass when you do, say, the parabolic approximation, right? Okay, now let's look at the papers. I saw that still the best way, I was checking which journals we don't know much yet. So let's still go back to applied physics letters. Okay. Applied physics letters is what's the recent issue? Current issue. Photonics, optical. So now if you look at first paper, long equilibrium longitudinal transfer of optical photons in terahertz quantum cascade lasers. Pretty timely, okay.
Yeah.
So what does it mean? I didn't read the paper, I look at title, I did look at the title, right? So what does it mean? My guess, okay, I was just say, sometimes I go there and take a look and say, I can guess what the paper might be talking about. And quantum cascade laser is a typical laser is you have a conduction band, you have valence band, right? And you put the electron, so you actually put a current, semiconductor laser. You put the current into here, you put a lot of electron from external injection, you put a lot of holes to here, and now electron will fall from here to here and give off a photon. That's the emission process, right? Of course, laser is stimulated emission. And this is a typical semiconductor laser. A quantum cascade laser is you use that, say, this is a conduction band, right? And typically, we just look at gallium arsenide. But when you make that gallium arsenide very thin, right, we have quantum well. We talk about the quantum well. So this is in 3D, right? Now, when you one direction, you make it very thin. So the energy start to discretize in that direction. So my wave vector spacing becomes very large, basically. Okay? And so it doesn't use the electron to hole recombination to generate photon. It actually uses the energy level in quantum well go from electron to generate photon. And the cascade down, the next quantum well is the same. So the photon stimulate, emit another photon, so that's a quantum cascade laser. But say, what it must be is, say, in the emission process, you have light, you have, say, electron, you have photon. So some of the electron will interact with the photon, with the lattice vibration. And in this process, when we go to, let's take a look. So you could dump a lot of energy to optical photon. Optical photon, and if they can scatter with acoustic photon, they will become, say, at a different temperature, drive out of equilibrium from the acoustic photons. So different modes, they could have long equilibrium. Let's see, what does this paper say? Experimental long equilibrium longitudinal photon and the interface transfers like optical photon associated with electron transport in resonant photon terahertz quantum cascade lasers. So how the this is the energy levels in quantum well. So this is the one quantum well, different quantum well, and the wave functions, or say in each quantum well, and okay. This is the, let's say, after photon, so it must be, this is probably the power. I don't know whether it's electrical power or, but looks like it's the Raman. So after experimental longitudinal mass structure, took a measured photon. You see, they must be using Raman to measure. See, this is a laser comes in. So what a Raman process? A Raman process is when you have photon disperse. So you have crystal, right? You have a laser comes in, and now the light of the laser, you have energy h nu, right? Now the photon energy is very small. It's say about 10 to 20 millielectron volts. Argon laser is about 0.5 micron, so it's about 2.5 electron volts, right? So, but this light can interact, say, with the photon, and then shift the scatter light. The frequency could be shifted. So this is a say plus minus h bar omega of the photon. So with that, you can measure the photon equivalent, say, population by looking at its temperature, all those stuff, right? And so that's an example of photons, and I'm sure I think I should stop. But if you look at it, there are actually quite a few papers in this issue journal. On the next few papers also, I saw photon topics, right? Okay, stop here.